Hi, my name is Giliard Godoy, and today I am going to present our work, a graph-based crossover and soft repair operators for the Steiner Tree Problems, which has been developed together with the Professor Renato Tinoz and Danilo Sanchez. Currently, I'm pursuing my master's degrees at the postgraduation programs in informatics in the Federal University of Technology, Paraná, here in the city of Coronel Procópio. Today I'm going to talk a little bit about the Steiner Tree Problems and graph, a new kind of partition-based crossover for Steiner tree. The experiments were made to validate our proposal, and the results we got, and some conclusions. The Steiner tree problems in graph aims to find a subgraph that connects a subset of terminal nodes, here represented by these orange dots. For that, it might consider some non-terminal nodes, here represented by these white dots or white nodes, and there are 2 points are worth to mention. First, any inner cycle can be broken in order to reduce the solution costs. As well, any leaf node that also is a non-terminal node can be removed without loss the connectivity between the terminal nodes and reducing the solution costs. One thing also is that this problem is defined for an undirected and waved graph. And these ideas can be used in a lot of application problems, such as multicast routing, phylogeny tree identification, subnetwork identification, and so on. However, the STPG is an NP-hard problem, which means that several algorithms and strategies has been developed to find better solutions for the general case, and some of them are based on in generic algorithm. But generic algorithms are not so competitive with more traditional approaches. And one reason might be because tree representation is not trivial for generic algorithms, like in other problems. And traditional operators might lead to unfeasible solutions, like disconnected subgraphs. One individual can represent a disconnected subgraph. One kind of operators work directly with the graph representations of the candidate solutions, like the partition crossovers. The partition crossovers were originally proposed to recombine Hamiltonian cycles for the traveling salesman problem. And they basically work in this way. First, they take two parents for recombination, join their edges in an union graph, as shown here in the figure A, and then it removes the common edges here and generates partitions, like shown here in the figure B. For each partition, it chose the subset of smaller edges to form the offspring. The common edges are transmitted directly to the offspring. So here in the figure C, in the top, it have been chosen the edge from parents in blue, and in the top, it have been chosen the edge for the parents for the red parent. And partition crossover has some interesting properties, like they transmit alleles, which means that all the edges in the offspring belongs to one or another parent, or both. There isn't an edge in the offspring that doesn't exist in the parent, in one of the parents. They are also respectful, which means that all the common edges are transmitted directly to the offspring. And they are also deterministic, which means that giving two parents A and B, every time the partition crossover is applied, it will generate the same offspring, because it explores this structure of the parents. And related to that, there also has this property of tunneling between optima, which means that if two parents are local optima, the offspring will be also will also be a local optimum with a lower cost. This true properties is kind of strange when we talk about genetic algorithms, because most of the crossover operators are random, have a random behavior. But the original procedures for the partition crossovers need to be adapted to handle Steiner trees because they differ in the topology. They have different topologies. For instance, let's pretend we have two Steiner trees represented here in the figure A and the figure B, and then we join their edges and remove the common ones, and we might get a subgraph formed with only one component, here in figure C. But how we can select the subset of one of the parents in order to generate a better offspring? So we decide to explore the common vertices as cutting points to break this component in smaller partitions. Notice here in the figure D, we have a component formed by common edges. These common edges are transmitted directly to the offspring, and we might think them as a unique node. Why? Because two candidate partitions to recombinate, they might connect to this component of common edge by different edges, by different vertices. Like here, we have a partition that connects to the vertex 23 and another that connects to the vertex 12. The nodes 12 and 23, they are connected by common edges. So we identify an inner cycle, and we now can compare these two partitions and choose the one with the lower cost. When we update the information about the connectivity between the common vertices in order to find more opportunities for recombinations, like showed here in figure F. These partitions only can be compared because we decide for the better partition here in the figure E. So when we decide here in the figure E, we can find more opportunities for recombinations in this figure F. And we come up with the final offspring. So our algorithm has two main stages. First, it identifies the common vertices and how they are connected by common edges. Then we identify the candidate partition to recombination using a breadth first search, and then we pass to the stage of matching the partition. We see which partition can be compared with another. We select the partition with the lower cost, and then we update the information between the connectivity between common vertices. By the end of this process, some partition may remain unfeasible, and we have chosen that we will generate two offspring, which one has the unfeasible partitions of one parent. So we return two offsprings. The experiments we made. We use our crossover partition in a generic algorithm, and we compare with two other generic algorithms. The first one uses random versions of pruning algorithm as a crossover operator, and another used binary representations for the Steiner trees and was implemented according to this work of Capsalis. For the partition-based crossover and the pruning-based crossover, we use generic algorithms. We use two soft repair operators. These repair operators, they do not try to fix the solution in a sense that they do not try to reconnect subgraphs because all the solutions are trees. They only try to improve the solution cost of the tree, of the individual. And how? The first procedure computes the minimum spanning tree from the subgraph induced by the solution vertex, which means they replace some adds by lower cost adds in a greedy fashion way. The second repair operator prunes or remove all the non-terminal nodes that are leaf nodes. They have degree equal to 1, like I said before. So we run 3 experiments 50 times over 18 instances. And in this first table, shows that our partition crossover achieves the better average solution cost in 9 instances. In some of them, it finds the best possible solutions in all runs. The print-based crossover finding 8 cases and the binary GA in 3. Regarding to the execution times, our partition crossover was better in 13 instances against 4 in the print-based crossover and 1 here in the binary GA. This table also shows the success rates, and the partition-based crossover was able to find the better possible solution for all instances at least once. Here in this instance, B14 to B16, the print-based crossover didn't find the best possible solution in any run. So, the two software pair operators, they really can improve the GA performance. The partition-based crossover achieved the best average solution cost for 9 instances against 8 and 3. And it also finds the best possible solution for all instances, for all problems. And had a success rate of 28% in the worst case. It was the fastest algorithm compared to the other GAs in 13 instances. So, our partition-based crossover for Steiner trees has this property of tunneling between optima. But it also converged very quickly to and lost the population diversity. So a mechanism to control the diversity of this might contribute to the GA performance to get better results. We also believe that we can improve the procedures of our algorithm and in order to make it more efficient, like have happened to the original partition crossover, which has been developed across several works. And we also have to test our operators in bigger instances, in bigger graphs, and compare with other approaches, maybe. These are the references I cited in this presentation. And there is a Q&A session, a questions and answers, 5 minutes for questions and answers. Feel free to ask me anything. Or you can contact me at my email address, giliardgodoy@alumnus.utfpr.edu.br. Thank you everybody for this opportunity, and I hope you understand me. Talk in English.